Ladies and gentlemen, we're going to begin our exploration of chapter 7, which is called Alkynes. Here is an alkyne. It's on the end of a chain, so it's called a terminal alkyne. Later on activity 2, we'll see some internal alkynes. They're in the middle of a chain. You got one already? Good. And we're gonna do some old stuff here, like way old. Test 1. We're gonna label each bond. Remember that? Yeah. Make sure you get that activity right there, Mr. Nasruddin. And we have this type of bond, which is the same for every label of C bonded to H except for the one on the very end. And we're doing A here. Sadly, my label A. There'll be a label B soon. So A, what kind of a bond is it when there's only one bond? Is it a sigma or a pi? Sigma. What orbitals were used to make the sigma bond? One came from the hydrogen atom, and what orbital is that? S. And the other came from a carbon that had 4 sigma bonds and no lone pairs. Yeah, sp3. We're remembering. I like. Okay. And B. First of all, this is part A. And label A was in part A, which is confusing unless I try to clarify. It's also a hydrogen, so there's an S. But the carbon right here, right there, has but 2 sigma bonds and no lone pairs. What's the hybridization? It's SP. In this morning's activity 1, we had a question: which of those is a stronger bond, A or B? And I'll just verbally give the answer because I wasn't asked the question here. It was B, because this hybrid is 50% S, which is closer to the nucleus than this hybrid, which is only 25% S. See how there's 4 parts in the name? Only one of them's S. Remember, orbitals in an S, electrons in an S orbital are closer to the nucleus than those in a P. For hybrids, it's kind of the same deal. The higher the percentage S, the closer the orbital is to the nucleus. And that makes the bond stronger, right? When you're closer to the nucleus, you're a stronger bond. You're a shorter bond. Okay, there's your bonds A and B. And I guess I didn't put a parenthesis out here. And let's do C, D, E. C is also a sigma. And the hybrids on both carbons are the same, aren't they? What are they? Yeah, sp3 on one carbon, sp3 on another. And D is different, right? Sigma sp3 on the top carbon, sp on the bottom carbon, and then E is the last sigma bond. It's a sigma between 2 SPs. That's the strongest sigma bond there, isn't it? On the whole page, E is the strongest sigma bond. And we have dessert is pi. Pi's for dessert all the time. We're gonna have F, and the second one we can't call F. We gotta call a different name, G. And what kind of bonds are the ones that are after the pi? Sorry, after the sigma. I gave the answer in my question by mistake. Sorry, it's pi. So they're pi bonds, the green one. What orbital makes pi? It's easy to remember. If you remember the Greek letter pi starts with the letter P, you have the answer to the question, what orbitals are used to make pi? P. And it's not that simple. Just P to P, you're going to lose a quarter point. You got to tell me you know the P's match or else they don't overlap. So what do you want for your labels? You like XX? And then for the next one, you can't use PX again because you already used it. So just pick another two that are matching. You like Z? I'll go with Z. I know why the guy likes Z. No, his last name doesn't start with a Z. That was close. S versus Z. PZ. Okay. Next. So I think we did part A. Geometry we'll do with a different color and capital letters. How's that? I think A is the same as this A, right? So we're doing part B. Then we can squeeze it in here. Big capital A. What's the name of the geometry when you have 4 sigma bonds? Tetrahedral. And what's your angle when you're tetrahedral? And then, careful. We can do better than that. 109.5, right? The tetrahedral angle. 90 is too close. That's A. And B and B are the same. Big B, what's the name of the geometry? Linear, yeah. And what's the angle for linear? Yeah. 180. Okay, which hydrogen reacts first as an acid? I'm just going to go like this. I know I skipped C. I will come back to C. That's the answer to that question if you like non-verbal answers. And give me the pKa for part C. We'll go pKa's in purple. pKa for a terminal alkyne, basically. Now my part A is in the way. There we go. What's the pKa for that alkyne H? No, that's an alkene. 25. Oh, I keep moving my stuff. Stop moving stuff. I want my pen, that's why. And the other H's, can we just highlight in a different color? Because all of them are the same green highlighter. Those are alkanes, aren't they? All of them are. And that was somebody said 50. I heard you. Yeah, you were right. Green ones, pKa equals 50. Oh, I can't use a green highlighter and a green pen. Maybe I can. Let's see what it looks like. It's gonna be subtle. Light green highlighter. Yeah. That works. Okay, yeah. And the pink one goes first because much lower pKa. That's what lower pKa means, right? Now we're going to take our molecule and do the acid-base reaction with a specific base. I'll save you some time. Those are a pair, right? Which one of the two is that I just connected is the acid? On the right side. And what's its pKa? Yeah, pKa is 35, which means you can calculate its pKb right now for the conjugate base. That's a wicked strong conjugate base, isn't it? -21. Wow. You need a strong base to take the H off of an alkyne. Negative. Make sure it's negative. And what about the, well, we don't know if it's an acid or a base, but we're going to be figuring it out pretty soon. If this was an acid, then it reacts with a base. pKb equals 14 minus, and I'm just going to look ahead. The number is 25, isn't it? I mean, the pKa was 25. It's the same molecules above. And that is still a strong base, but not as strong as that one on the left side. Circle the favorite equilibrium arrow. Well, clearly I forgot to do this. Give you 2 arrows. And I really didn't have to add that second one, did I? Wow. I thought I got the smaller 8. I was wrong. I'm trying to give it a trim here. There you go. You do like the forward arrow. Tell me why. Why do I like the forward arrow? Stronger to weaker is a good answer. Yeah. Yeah, circle it with red and green. I based my decision on the 2 pKa's, red and green. 25 goes to 35 every day of the week. And basically, you're just going to draw me the conjugate base of the species listed there. Don't take any of those H's off. Their pK is 50. Don't take any of these H's off. Their pK is also 50. Don't forget H plus off, leaving a minus behind. There you go. So we gave pKa's for the 2 acids, we gave pKb's for the bases. We filled in the missing piece, we circled the favorite arrow. We're going to calculate pKeq. pKeq, left acid minus right every time, no exceptions. That's the equilibrium favoring the right side. Now we know how much by. 10 to the 10. There are 10 to the 10 times more products than there are reactants. That's what that means. Good review activity. Might consider that a double activity, you never know. Stopping the video if I can.